Back to this NPTEL online certification course in molecular rearrangement and reactive intermediates. So I started talking about nitrene from the last class. I talk about different method for the nitrene generation. I talk about their comparison with the carbene, and I also talk about the singlet and triplet nitrene. In the today's class, I am going to talk about several other reaction like the insertion reaction and several different rearrangement reaction using nitrene. So I am going to talk about first about the insertion reaction, and then I am going to talk about the rearrangement reaction of nitrene. Then I think the 1,2 alkyl or aryl shift. I think these are the very important rearrangement reaction, Cartier, Lawson and Hofmann. I am going to talk about all of these different rearrangement with some of the examples. So let's start with the first thing is the the reaction of nitrene, and the first thing is insertion reaction. So we have learned about the carbene insertion reaction, and I think I already talked about in the carbene that the reactions when happening from a singlet, you have seen the reactions are very much stereospecific. That means if you start with a chiral center, that means that particular chiral center will be remain intact here. Only the CH will be replaced by NHR. Okay, that means this reaction is happening through a concerted mechanism. That is another important thing. So this CH insertion which is happening through a concerted mechanism here. That is why you can see this reaction is stereospecific. That means the stereochemistry will be retained. So there will be a retention in the stereochemistry. Okay. So which is actually mentioned here, the reaction is inserted CH bond in a stereospecific and a concerted pathway. So let us see some example here. Okay. So here I think an example, again the same thing is mentioned here, that if you generate a nitrene and if you have a saturated hydrocarbon, I think I have explained very similar thing in case of the carbenes. Here you can see also the nitrene is going to through a concerted pathway it is going to generate the corresponding the amine. So here again from cyclohexane, this CH bond actually getting inserted into this nitrene to form this compound. Okay. So it is forming some sort of a carbamate after the CH insertion. Again there is an example here. I think one thing, if you remember when I was talking about this type of CH insertion, I always try to show you the corresponding some sort of a tangent state. And in case of carbene, you have seen how this tangent state is very important, because there is a steric factor sometimes also getting to a dominating factor. So there is a three different type of, there is a different type of CH here. One could be the methyl, which is going to be your CH3 going to be a primary. Then you have some sort of a tertiary CH here. Then you have a benzylic CH here. Okay, so these are the different type of CH is present, and the reaction is happening through abstracting of this benzyl CH. So this the abstraction from the benzylic is the minor product, and then abstraction from this hydrogen, the 3-degree hydrogen, is going to be a major product. So I think from this result we can clearly see the electronics actually play an important role. That means the CH insertion happening from the CH group, how much electronically rich, that is a one important factor here. Okay, because here it is abstracting from this one, so this hydrogen will be more electron rich compared to the corresponding the benzylic. Okay, so that is why you can see the the abstraction is happening from this particular CH is getting abstracted to from this product as a major product. Okay. Then there are some other example here, the thermolysis of cyanogen azide. So I mentioned in the previous class that we don't see too many of alkyne azide or alkyne azide from formation of alkyne based nitrine, but from cyano it is kind of well known that from cyanogen azide from thermolysis it can generate the corresponding nitrene here, and one is generating this nitrene which now can go for insertion. Now you can see, so this is a 1,2 dimethyl cyclohexane which are cis. So it is actually stereospecifically abstracting the CH which is from here. Okay, so it is abstracting this CH, this CH one, as you know that this is a tertiary CH, it will be electronically rich. So it is going to abstract it in a stereospecific manner to form this product as a major product. Again very similar thing here, if you start from a anti 1,2 dimethyl cyclohexane, again you can see the abstraction is happening from this proton here. So it is abstracting this proton, this CH proton, again the one from tertiary electronically rich. So it is giving very stereospecific product. because again this reaction is actually happening because because this is a singlet nitrene. So if it is a singlet nitrene, then the reactions will be stereospecific, the CH insertion. And then there is another example here. So this is a very common example, you can see in a lot of time in the exam. So this is a alkyl CH, okay. So which is, so now you have a chiral center here. I mentioned at the beginning that if you have a chiral center, then there will be retention in the configuration after the CH insertion happen here. So what happened at the beginning, after the thermolysis, it will go to generate the corresponding nitrene here after the expulsion of the N2. So this nitrene is now abstracting this CH bond here, and so there will be insertion and to form this product with a retention. There is another example here. You can also able to generate some sort of a rhodium based nitrene. So here using the PIDA and then the rhodium tetraacetate, it can generate the corresponding nitrene. Now the nitrene is abstracting this, again this proton, you can see there is two different sides. There is a benzylic proton here, it can also abstract from this side or this side, they are both symmetric, okay. So it can abstract the proton and going to form this product as a major product. There is another example here from aryl CH. If you are actually generating a nitrene after the heat or H nu, then that nitrene will going to abstract this aryl CH. So there will be a CH insertion here in the nitrene to form this intermediate, and then from there a 1,5 hydride shift, there will be so you can give them 1, 2, 3, 4, 5. So there will be 1,5 hydride shift actually end up making you the corresponding carbazoles, okay. So now I am going to talk about some other reaction. I think I mentioned at the beginning that if you go for some sort of a generation of nitrene, there is one of the major things it can dimerize if you don't have anything else, like if you don't have any olefin where it can able to form a aziridine, then in the absence of that it can form a dimer. Very similar thing happen if you have a aryl nitrene species, you can also form a dimer, okay. There is other thing happen if you have this type of scenario when you have some sort of a formyl group attached with the nitrene, then there is a possibility, because once you generate a nitrene, now you can think about them as a 1,3 dipole, because you can see there is a electron density here, and to one side in the next to the oxygen there is electron density and the other side there is electron deficiency. So this is a 1,3 dipole going to participate with the cycloaddition with the corresponding cyanide to make this oxadiazole, okay. And then you can see some of the reaction with oxygen and sulfur atom. So we have learned about this halide chemistry when you talk about carbene. If you remember, we talk about halide chemistry, that the oxygen lone pair of a carbonyl group interact with a carbene, and then they can participate in a 3+2 cycloaddition reaction. Here something is going to happen. So if starting from this reaction, if you use a sodium azide in DMF, it will go for SN2 reactions. You can clearly see that. So this bromide is going to get replaced, and then what is going to happen? There will be elimination to generate this compound, and now what is going to happen? This is going to generate a nitrene. So once it is going to generate a nitrene here, so you can see there will be N2 expulsion to generate a nitrene. And once it is generating nitrene, the oxygen lone pair, as you know, the nitrenes are electron deficient. So the oxygen lone pair is going to give electron density into that empty p orbital, okay, to finally able to form this type of heterocyclic compound, okay. There is another example here. So you can see again very similarly, there will be first thing will be after the thermolysis of the pyrolysis, it will generate a nitrene. And you have a oxygen here, so oxygen lone pair is going to give electron density to that empty orbital here in the nitrene, that will generate this type of intermediate. But you can clearly see now there is a negative charge on the nitrogen, which will able to take this methyl group to release the positive charge from the oxygen to get to this type of heterocyclic compound. Now there will be some other reaction called the rearrangement reaction of nitrene. So there are 1,2 alkyl and aryl shift. So we talk about this type of 1,2 alkyl shift in aryl shift in case of carbocation, if you remember. Then I talk about carbanion. I mentioned that the 1,2 alkyl shift are not favorable, but the aryl shifts are favorable because of generation of the more stable carbanion. Here I am going to talk about in case of nitrene also what is going to happen. Once you have a 3 alkyl group here, if your R1, R2, R3 become a alkyl group, then there will be alkyl or aryl, then there will be, or if you have a hydrogen alkyl, so there could be different scenario. If you have a hydrogen and then alkyl, then there will be hydrogen will be shift will be happening faster than the alkyl. Okay. So this is the rate of, so the first the hydrogen, then the aryl, and then the alkyl. Okay. So this is happening here, so as you know that once this this sigma bond electron density is given to this empty p orbital in the nitrene, at the same time nitrene has the pair electron, it is going to transfer to the corresponding sigma star orbital to get to this product. Okay. So this method is very useful to convert alkyl halide to corresponding carbonyl compound. So let us see how it is happening here. Starting from alkyl halide, you can do SN2 reaction to get to this corresponding azide. Now you know alkyl azide, after the thermolysis it is going to generate the corresponding nitrene. So there will be 1,2 hydride shift for this, this H going to move here to generate a imine. Now imine in place of water can hydrolyze to corresponding carbonyl compound. So starting from alkyl halide, you can generate a corresponding ketone using the nitrene chemistry. So here is an example, instead of the alkyl and the hydrogen, you have a triphenyl. If you have a triphenyl, then after the formation of this corresponding nitrene, as I mentioned, the phenyl group going to get migrated. So there will be 1,2 aryl shift to form this corresponding imine. Okay. So there is another example here. If you have a trimethyl group here, if you have a trimethyl and then corresponding azide, then it can form the corresponding nitrene. Then there will be a 1,2 methyl shift here to generate this type of imines. Okay. So if you have a 3 alkyl or 3 aryl, that will be 1,2 aryl or 1,2 alkyl. But if you have a hydrogen with a alkyl or hydrogen with a aryl, then the shift of the hydrogen will be faster compared to the alkyl or aryl. So now I am going to talk about a very important rearrangement reaction where there is a generation of nitrene species. So that is called the Cartius rearrangement. It was discovered by Theodore Cartius around the 1890. So this is a very important reaction because starting from acyl azide, once you put heat, it can generate the corresponding isocyanate. This is a very important intermediate species. Once you treat with the water, it can generate corresponding amine. Once you treat with the amine, it will generate corresponding urea, and then once you treat with the alcohol, it will generate corresponding carbamate. And this type of acyl azide is easy to make starting from corresponding acyl chloride or corresponding acid. Okay. So it can easily mate, and then you can able to generate the corresponding isocyanate, and now depending on the nucleophile you choose, you can able to access a variety of compound. Okay. So in this part I am going to talk about the mechanism of the Cartius rearrangement here. So what is happening here, you can see first thing, once you generate the acyl azide, we can try to draw the canonical structure here. Now you can see here, now this minus which is here in the azide, that can give the electron density here to make it as a O minus, some sort of a species here, O minus, and then it will come back again here and it will going to get migrated to the nitrogen and expulsion of this N2. Okay. After that it can go through some sort of a tangent state like this, where what is happening, there is a there is a cleavage of this carbon and the R group, there is a cleavage of this the N2. Okay. And there is a formation of some sort of a double bond between the carbon and nitrogen, which is shown here. After that it will generate the isocyanate. As I said, if you treat isocyanate with the water, it will generate the carbamic acid. Now you can see in this reaction, you will see generally in this reaction there will be a base present which is going to abstract this H here, and then after that what is going to happen will be a decarboxylation. There will be decarboxylation under presence of the heat to generate the corresponding amine after the protonation. Okay. And then if you treat with the alcohol, it will generate the corresponding carbamate, and depending on the alcohol you can vary different type of alcohol to get different type of carbamate here. And most likely this this rearrangement goes through a concerted process. Okay. Although we try to show this type of arrow pushing mechanism, but this reaction goes by a concerted mechanism to form the isocyanate. Some example here. So if you start from a chiral acid, then this the configuration remains same. That means there will be retention. Okay. Whatever the stereochemical information there, which is going to remain same after the Cartius rearrangement. Okay. So first thing what they have done, they treated with the SOCl2, so that is going to pyridine and the thionyl chloride going to convert this corresponding acid to acid chloride. Now once you treat with the corresponding sodium azide, it will generate this corresponding alpha ketoazide, and now in place of xylene and heat, it is going to participate in the Cartesian rearrangement by forming the corresponding isocyanate, and I am sure in this reaction there will be some water already present. So as the water is present, which is going to convert, after it is going to go to the carbamic acid, and then it is going to convert to corresponding amine. Okay. So this is an important method, because you starting from a carboxylic acid, in one step you can able to convert to corresponding amine. So there is another example here, starting from this type of pyridine carboxylic acid, using DPPA you can able to convert this corresponding carboxylic acid to corresponding azide, and then you can able to, so there is a heat given to this, so that means this acid will convert to the corresponding, not only corresponding azide, it will go to corresponding isocyanate. Then there is a methanol present here, which is going to make the corresponding carbamate here. Okay. There is another reaction here, in this synthetic transformation you can see you have a carboxylic acid here. So first again formation of the corresponding acid chloride, then using the sodium azide it will form the corresponding acyl azide, then under heat it will go for a Cartesian rearrangement to form the corresponding isocyanate, which will once react with the methanol, it is going to form the corresponding carbamate here. So it's a very simple thing, you first convert the corresponding acid to acid chloride, then corresponding acyl azide, under heat it form the isocyanate. Now you choose different nucleophile. If you use alcohol, it will going to form the corresponding carbamate. There is another example here, you have this carboxylic acid going to convert to acid chloride, again azide, formation of the isocyanate, in place of H2 it is going to convert to corresponding amine, and if you give some acid there at the end, then you can isolate the amine as a protonated form, as a salt. So now there is another synthetic application again here, using DPPA and triethylamine. So this is a diphenyl phosphoryl azide, which can able to convert this corresponding carboxylic acid to the azide, then corresponding isocyanate. So now if you choose this corresponding alcohol, it will going to make this particular carbamate, which you can use for further transformation to make a biological active compound. There is other example here, you have a carboxylic acid here. Now you can see this, they have a trans relationship, and you can see this stereochemical things will be remain intact. So you can see this will end up making this corresponding corresponding carbamate, and here also you will see their relationship remain trans. Okay. Because you can see the most of the things happening on the carboxylic acid, not the carbon attached, because because once the migration is happening, that stereochemical information still remain retained. So that's why there will be a retention of the configuration. So again I think I have explained corresponding isocyanate first, and then you can able to make the corresponding carbamate, which is going to give it to this corresponding natural product. I am going to move to the Smith reaction here. So Smith reaction is another important reaction. So starting from the carboxylic acid, using the hydrozoic acid, it can able to convert to corresponding amine in place of acid and water. So now we are going to try to learn what is happening here. If you using carboxylic acid, once the hydrozoic acid actually react to the carboxylic acid, then it is going to make this type of, so it first it is going to react form this species. I said this is a carbamic acid. So then what is going to happen, there will be a minus CO2, so there will be decarboxylation going to happen. I have already mentioned before, to get to this corresponding amine. Okay. And if you have H plus, it will make a corresponding amine salt. Okay. There is another example here, if you have the NaN3 and the polyphosphoric acid, it can able to convert to this corresponding amine. So if you have a NaN3 and a phosphoric acid, that can generate HN3 inside, okay, inside the reaction. So ketone are converted to amides when treated with the hydrozoic acid. You can able to convert a ketone to corresponding amide. So that is a very important transformations, okay, using hydrozoic acid. Again you can see in the mechanism what is happening. First the hydrozoic acid going to give, so the nitrogen of the hydrozoic acid going to get attacked here to form this type of species after getting protonation. And then what is going to happen, this oxygen lone pair going to push back the electron density, and there will be a 1-2 shift of this R group from this carbon to the nitrogen, then elimination of the N2 will generate this type of amide. Okay. Again here there is a intramolecular example. It's not that always you have to be a protic acid. So if you have some sort of titanium tetrachloride, then the reaction can also happen. But here is an example of an intramolecular reaction. You can also able to get to this corresponding lactone. There is another example of Smith reaction here. You can see there is a C4N3. If you treat with the titanium tetrachloride, very similar thing going to happen. The mechanism is given. This N minus is going to get attacked to the carbonyl. Then there will be a Lewis acid which is going to take with this oxygen, and then it is going to come back, and there will be a what is happening at the end. You can see this ring is getting, so this ring is getting expanded here, okay, to form this type of product. So what is happening at the beginning? You have a 7 member here, 1 2 3 4 5 6 7, and you have a 6. So here what is going to happen? So this is going to become a 7 member, and this will be a 6 member, okay. So there is another example here. You reacted with this type of species with the, so this is a gamma hydroxyazide. When it's reacting with the carbonyl species, first it is forming this compound. It is reacting to the alcohol, and then what is happening? The nitrogen of the azide is attacking here, and then it is cleaving this, going for a ring expansion to cleave this nitrogen bond to get rid of the N2 to form this type of intermediate species. Now the water is going to get attacked here, okay. So water is going to attack here in this position, and then after that it is going to form this some sort of a lactone again. Okay, so previously I talked about the Cartesian rearrangement and the Smith reaction. Now I am going to talk about the Lawson rearrangement. Okay. So now what is going to happen? This is a conversion of O-acyl hydroxamic acid. So starting from this O-acyl or some sort of, so you are starting from the hydroxamic acid. You use a acylating agent to make this as a leaving group. So you want to make this part as a leaving group. This can be denoted as a leaving group. Okay. So once you have the leaving group, now you become a O-acyl hydroxamic acid, which in place of heat or in place of base, in place of heat or base, it is going to form the isocyanate. Now the nucleophile can attack here, as you can see, very similar to the previous rearrangement reaction, and to form this corresponding product. So this product can be vary, as you know, starting from isocyanate, depending on the nucleophile. If it is a water, you can able to make the corresponding ammonia, corresponding amine. If it is a water, and then if you use a corresponding alcohol, you can make corresponding carbamate. And this is the mechanism again. So first the base is going to abstract this NH proton, put a negative charge on the nitrogen, then you use a corresponding acyl. Now you can, what is going to happen? It can go for some sort of a mechanism like that, where it can become a O minus, then this one get migrated here, this can go for a leaving group to get to some sort of a tangent state to the corresponding isocyanate. Okay. So here is an example of Lawson rearrangement. So what is happening? Starting from this, you can see you have the starting material already here. So here if you use a acetic anhydride and pyridine, it can make it a very good leaving group. Now just you need a base to make a deprotonation of this NH. So that will allow this the one to shift, and then you have already a water. So you are forming isocyanate, which is going to treat with the water to generate corresponding amine. Okay. There is another interesting example here in this molecule. If you see, you have this type of species here, which you call isourea, which is already attached with the oxygen. Again, you just need a base to abstract this proton here to make N minus. Once you go for the minus, this can go as a O minus. It will come back, and there is a one to shift, and then it will go for act as a leaving group. It will generate the corresponding isocyanate, which can treat with the water to generate a carbamic acid. Finally, after the removal of CO2, you will generate this corresponding amine. Then I am going to talk about the Hofmann rearrangement. So this is conversion of primary carboxyamide to the corresponding 1 carbon shorter amine. So what is happening? You can see we are starting with the RCONH2 to RNH2. That means in the end, what is happening? We are actually getting rid of this CO from the starting material to the product. So what is the reagent? You have to use NaOH with the Br2. So what is happening? The role of NaOH is actually to after the proton from the NH2 form this species, which is now what is happening? Now this is going to make a N-bromo species here. So it can come back and take a bromine here, and now in place of base, it is going to take this proton to make a anion here, which can go for formation of the O minus. It is going to come back, allow this one to shift. Okay, it will generate this corresponding isocyanate again, and now once you treat with the the water, it will generate the carbamic acid, which after the decarboxylation, it will generate the corresponding amine. There is another example here. So what is happening? Some sort of a amide, you will end up making to the corresponding amine. Okay. You can think about like conversion of benzamide to corresponding aniline. I think if you think about the mechanistically, this is the very similar. I think you might see this type of transformations comes in the exam. So here what is happening with pyridine, that is happening that with KOH and Br2 it is actually converting to the corresponding amine. Okay. So the Hofmann rearrangement is intramolecular or the intermolecular. That means if it is this NH2 which is forming at the end, it is coming from the other source or it is forming in the same molecule. You can test this using this type of starting material. So one case you have a deuterium at the meta position, one case you have started with the 15 level nitrogen. So what is happen at the end, you end up getting this product, not this set. So what is this one telling you? That okay, this is telling me of course this NH2 is coming from this UNH2, and in case of the 15 level one you end up getting the aniline which is the nitrogen is 15 level. Okay, so this is going for a intramolecular, not the intermolecular. Okay. Then there is some example of Hofmann rearrangement here. You can see in this example what is happening. You have a carboxylic acid and you have a amide here. So it is actually interacting with the amide, abstracting this NH proton. Then there is a CONHBr first, and then it is going to abstract the NH proton, then formation of isocyanate, and there it will form the carbamic acid if you have a water here, and then it is going to finally form the corresponding amine. And now what is happening, as you have the corresponding, so generally this OBr minus comes from if you have a KOH and Br2. As you have KOH, it is can abstract this acidic proton, and in case of Br it can form some sort of a COBr which can go into form a cyclization between this amine and the acid bromide which is going to form to make this corresponding product. Okay. So one of the important fact is that if you start with this amide which has a chiral, if you start with the chiral amide, again there will be retention, okay, after the reaction. So means what is happening, as I said, this group is getting migrated, so there is no change is happening in this particular configuration. So that configuration remain retained in the product. So there will be retention happening. So what we have learned in this course, in this part we have learned the singlet nitrene insert into the CH bond. So I talk about different insertion in reactions, and then I talk about this 1,2 shift of alkyl and the aryl, and then I talk about the Cartier's, Hofmann and Lawson rearrangement. And so this is a very important topic, because you will see a lot of questions from carbene is coming from this rearrangement. These are the reference for this topic. You can able to go through the Claydens in the Advanced Organic Chemistry by Cary Sandberg, and this is a very important book for reactive intermediates. Thank you so much for coming to the class. I am hoping to see you guys in the next class. Thank you.